So welcome everyone, my name is Doug Schmidt and I'm looking forward to spending the next 30 to 45 minutes with you giving a talk about architecting systems of the future, a research agenda. And then of course there'll be time for questions at the end. So let's go ahead and take off and get started. So it's pretty clear to anybody in our field that there's a growing dependence on software-reliant systems that makes it imperative to continually innovate in software engineering theories, tools, and practices. And of course, I'll be focusing quite a bit here on middleware, since that's a research topic I've worked on for many years. But be aware, of course, that there's a bigger story here that involves other areas of computing as well. So, due to the ubiquity of software in today's systems, we have to figure out how to assure software continuously, because people are using these software systems for more and more mission-critical and safety-critical applications. And it's also important to be able to get new capabilities fielded as quickly as possible. We'll talk more about that in a second. There's lots of interesting trade-offs that exist in that space. Because of the challenges we face and because of all the new hardware and software innovations, it's important that we continue to innovate with respect to research. And that's because historically it's been very hard to get systems that will be better in the sense of more reliable, faster in the sense of better throughput, better scalability, and cheaper. You can pick any two of these. And we'd like to get to the point where you can get all three. You'd like to be able to develop systems quickly, they'll be scalable and efficient, and they'll be relatively inexpensive to develop. And we're not going to be able to get there just by using today or yesterday's technologies. So since it's hard to get these capabilities all at the same time now, the Software Engineering Institute, where I work as a visiting scientist, in conjunction with other groups such as DARPA and NSF, led a study to evaluate and reevaluate and define and redefine how we build software and what kinds of challenges and opportunities we're going to be seeing in the future. So that's what I'll be talking today about. And so the idea behind this is to catalyze the software engineering community by creating a multi-year, decade and a half, research and development vision, strategy, and roadmap to help us be more effective at engineering these next generation systems that we're going to be depending upon ever more and more as we go forward. You can get access to the report I'll be describing here at the link. I put this link into the chat, but you can also get this from the slides. I'll be giving the PDF version of the slides to Abhishek so everybody can take a look and see what I've been covering here. So this report has just come out basically maybe a month ago. And it's very interesting and has lots more details than I'll have time to cover in our time together today. So why do we care about a research agenda for software engineering? Well, hopefully it's pretty obvious. Software has been essential to being competitive, to being innovative, to being secure for quite a long time, and it's only getting more and more pervasive. Global economies, infrastructure, education, healthcare, national security, entertainment, all depend very deeply on software, as we've discovered in the last couple of years, as we've had various types of outages and ransomware attacks and so on. It's very clear that we are crucially dependent on software and how it works to be an effective society of the world. So if we want to increase productivity, if we want to be able to increase quality, we're going to have to do something more than the same old status quo. So one thing we need to do is identify what some of the future challenges are to engineer these more and more critical software-reliant systems, which everything depends on. What we've done in this study, which I'll talk about, is develop a roadmap that will help to guide and drive advances in foundational software engineering principles across different kinds of systems. So these are intelligent systems, autonomous systems, safety-critical systems, data-intensive systems, all the kinds of things that researchers in the middleware community and beyond are very much involved with. We also, of course, need to continue to raise the visibility of software to the point where it gets the same kind of recognition as other fields, such as medicine, commensurate with its importance to security and competitiveness. People sometimes think that all the high-tech companies are going to solve all the research challenges associated with next-generation software-reliant systems, and while they certainly can contribute quite a bit, they typically focus on things that are more product-oriented as opposed to focusing more broadly on building the underlying foundations of software. And that's, of course, where funding agencies and other activities at universities and research labs become absolutely crucially important. And we'd also, of course, like to find a way to get collaborations between different groups. We want to be able to have collaborations between academics, which many of us are involved with. Of course, we need to have industry collaborations as well, because that's where the technology actually gets applied in practice. And government has to be a key partner here because they provide lots of the funding, and they also have lots of the interesting problems, especially with large-scale systems, things like national-scale systems or systems that are going to be international in scope, and we'll talk about some of those as well. So what are the kinds of systems that require advances in R&D, and how does this affect people doing research in middleware and other technologies? Well, one example of a system type that's increasingly important are highly adaptive systems that focus on different missions. So think of things like trying to get to Mars or doing space exploration, where you don't know when you launch your system, your spacecraft or whatever you're launching, what exactly it will encounter along the way, because you can't predict everything that will be involved and integrated with this final approach. Another good example of systems that require advances in R&D are systems that perform data fusion at huge scale. Think, for example, of weather prediction. It's getting more and more important to be able to do weather forecasting for all kinds of reasons. A lot of those have to do with economics. They have to do with preparing for natural disasters, being able to route information, route goods more effectively throughout the global supply chain, which is a big problem at the moment, as I'm sure you're aware. Highly available business enterprises. So many things now depend on 24/7, 365 IT connectivity. Almost everything you do, everybody's ordering things online nowadays because they're less incentivized to go to the store. So having the ability to get access to information and be able to ship things in a cyber secure way is crucially important. Personal digital assistants that actually assist you and don't just give you a listing of what your calendar updates are going to be for the day, which isn't really particularly very helpful. That would be nice. That requires some insights in terms of intelligence and in user intent. Something that, of course, is crucially important, especially as major portions of our population age, our support for personalized, holistic healthcare that treats more than just the symptoms, but gets to the causes and can be customized for individuals at their molecular and genetic levels, or at least at their habit levels. And then something else I know is near and dear to the hearts of many people in the middleware community are support for smart stuff, smart cities, smart buildings, smart roads, cars, transportation systems, and so on. And again, it's as those of us who live in places that are getting increasingly packed from the point of view of people moving to the region, finding ways to be more effective with the road system and do a better job of routing information and routing people around. Very, very important for satisfaction in modern civilization, especially overcrowded civilization. What are some trends that are also motivating new R&D advances? Well, the need for safe and resilient software composition at scale is increasingly important. We're not just building small systems that work in isolation. We're building large systems that require safety critical processing and safety critical properties. Things, for example, like air traffic management, which are getting increasingly large and interconnected, or the power grid for that matter. We'd also like to be able to rapidly and continuously evolve software in an assured way. It's not enough to do releases once every 5 to 10 years the way that we used to do in many mission and safety critical systems. We need these things rolled out very quickly. If for no other reason, we have to respond to security threats that are ever growing and causing trouble. Another big challenge we have is not everybody who develops software is up to speed with the latest and greatest technologies. Even where there are people who are up to speed in the latest, greatest technologies, there's typically not enough of them with respect to all the work that needs to be done. So there's all kinds of workforce gaps where we have to find a way to be more effective at applying and in training and improving software talent from people. Some other things, of course, that are very hot from a buzzword point of view are AI-inspired automation, trying to do things that people used to do and have them done with machines. This, of course, is a trend that's been going on for decades in the software community, but it's only accelerating and perhaps getting more dramatic in terms of the effects of what happens when intelligent software goes awry. I've been watching Battlestar Galactica recently, where the Cylons rebel and take over the universe. And we have to be careful with stuff like that, obviously. Another thing that is a trend is evidence-based assurance that demonstrates a system behaves as it's intended to behave. This is a big issue for safety critical systems, of course. How do you provide enough evidence? How do you give people confidence that things work the way that they're intended? Another big issue, which we'll spend some time talking about towards the end of the presentation today, is the impact of so-called cyber social platforms. Think things like TikTok or Twitter or Facebook or YouTube on social behavior, creating societal scale impact. Think about the impact of deep fakes on all kinds of things, on celebrities, on governments, on the chance for misunderstandings to lead to regional or global conflicts. The list goes on and on. So social media and societal scale platforms have a big impact on many things today. And then something else that I just need to mention, because it's crucial to understand where we're headed, is that data is becoming more and more important for almost everything. As Abhishek mentioned when he introduced me, I'm also the co-chair, co-director of our Data Science Institute here at Vanderbilt. And it's very clear that data has become as important as code, as the software, when you think about building large-scale systems and having those systems create information that can be understood and interpreted in a meaningful way. So what we did to address these issues, we have an advisory board. If you take a look at the report, you'll see who the advisory board is. It includes some very well-known people like Vint Cerf and Bill Shirless and Deb Frinke and others. We also have some other colleagues from the Software Engineering Institute, such as Anita Carlton and John Robert and Dio Denise, Mark Klein, and so on, John Goodenough, very well-established experts in the field. So we surveyed the computing landscape, took a look at a lot of emerging technologies, did quite an extensive review of literature, interviewed a lot of experts, held some workshops, did a lot of future scenario imagining and visioning and so on. And we tried to get input from many different groups as we could. And this led to the report, which just came out recently, which is called Architecting the Future of Software Engineering. But again, you'll see it's more than just software engineering in the traditional sense. It's really about software-reliant systems of the future. And we wanted to do this in a way that people could act upon. And so what we're hoping to do, now that we've released a report, is help to influence policymakers and other folks who control the research funding spigots to help make sure that what we lay out in the report can actually come to fruition, because these things take time and they require a big investment. So what is the future of software and software engineering? What's it going to look like? Well, obviously over the last 40 or 50 years, a lot of things have been happening. And I would say in general, there's been a movement away from doing everything in a manual way, using low-level languages and low-level platforms and low-level tools and so on, to approaches that are increasingly abstract and increasingly automated. So that's pretty clear. I think that's been going on for a while. But what we think is going to happen over the next decade or so is that the traditional way of building software, which still requires a lot of people, will be one where the software pipeline, the pieces involved, consist of both humans, which is what we have today, plus AI elements as trustworthy collaborators that can rapidly evolve systems based on intent of the user, as opposed to having to specify and program everything manually. And of course, we've been moving in this way for a long time. You can think about model-driven engineering, model-integrated computing. You can think of middleware in many ways, or model-driven middleware, as basically steps in this direction for a while. But I think those trends are going to be accelerating. And these advances are going to be driven by improvements in both development paradigms as well as architectural paradigms. So let's spend a little time talking about the difference between these two themes, or these two constructs, and how they're going to be evolving. So development paradigms are going to be important to lead to efficiency and trust at scale as we build these bigger and bigger systems that we rely more and more on. So what are some examples of development paradigm advances? One is that humans will continue to leverage artificial intelligence as a workforce multiplier for all aspects of software creation and sustainment. So this is going to be all throughout the life cycle, from early requirements gathering to specifications to design and architecture and programming and testing and life cycle sustainment and evolution. We're also increasingly going to see formal assurance arguments being combined with other approaches to quality assurance and analyzed in order to be able to assure, and here's the kicker, efficiently reassure continuously evolving software. And this is particularly important for safety critical systems where historically it's taken quite a lot of effort to try to recertify them when any small changes occur. So we're trying to find a way to make secure and safe systems be produced more rapidly and more effectively and more cheaply than they are today. And then something else, of course, which is near and dear to my heart as a middleware researcher, is enhancing software composition mechanisms that enable predictable construction of systems at an increasingly large scale. So you can basically think about smart composition, which is a really classic middleware concept. So those are some of the development paradigms, and I'll talk more about each of those in a moment. There's also going to be architectural paradigms, which will enable predictable use of new computational models. So one of these computational models is actually kind of an interesting perspective. It's really thinking about societal scale systems or large scale socio-technical systems, things again like Twitter or TikTok or Facebook or YouTube and whatnot that influence the whole world, and trying to find ways that we can make these systems be more ethical, less driven by fads and panic and propaganda, in order to be able to get output and outcomes that we have better faith in and trust, using the word trust more in terms of trustworthy as opposed to being fake news, for example. Another key advance will be taking AI and non-AI components and having them interact in predictable ways to achieve the appropriate outcome and goals. This is really trying to use artificial intelligence fabrics that have a tremendous amount of non-deterministic reasoning behind them, and using them in ways that will be more predictable in their outcomes. So it's kind of the flip side of trying to use AI as a workforce multiplier. It's really trying to apply AI to good effect and relying on computing fabrics that don't have traditional properties in terms of predictability and dependability and the classic ways of thinking about them. And then the last piece of the puzzle here will be new architectures and analysis and design methods to facilitate the development of quantum-enabled systems. This, of course, is a big buzzword for a lot of people. There's a lot of focus on trying to build quantum-enabled hardware and coming up with quantum-enabled algorithms. But of course, at some point, if the hardware ever becomes a reality and the algorithms ever become a reality, we're going to need new platforms and middleware and operating environments in which to program and deploy and assert and certify those systems in sensible ways. So if you take a look over the next decade and a half or so, you'll see that there's going to be advances in all these areas, which will ultimately end up in a world, hopefully, where humans and AI are trusted collaborators that rapidly evolve systems based on user intent, if we do our job right. And this involves a number of different advances that are going to have to take place in all these different areas. Now, I'm not going to talk through each of these different topics in great detail because we don't have enough time, but if you read the report, you can find out the research roadmap and what innovations are required for each of these different thrusts. What I will do, however, is go into a bit more detail about these different development paradigms and architecture paradigms, so you have a better sense of what I think are some of the research aspects that are going to be important for next generation researchers, such as those of you in this doctoral symposium. So you can see here the first one is termed AI augmented software development, and the focus of this research area will be on using AI methods, tools, techniques, and so on to improve the software development process itself, especially trying to take things that right now are done in a very mundane and manual way and trying to find tools that will automate large amounts of those. Now, again, some of this stuff is just building off of things that have been going on for decades, but others are perhaps more novel, trying to be able to do things like intelligently search large databases of software repositories like GitHub, for example, or pick your favorite source code control system you might use on your projects and analyze it to look for ways of understanding requirement drift or issues of quality where there may be different groups of people who don't quite understand what the requirements are, how to achieve the requirements in the code base, and so on. So there's lots of opportunities for tools that will do those kinds of analyses in the background and then provide meaningful results to humans in ways that we currently can't do effectively because we get bored and get sloppy. Another very important topic here is assuring continuously evolving systems. And as we'll talk about in a moment, this really involves developing theories and associated practices that allow us to be able to rapidly deploy assured software in safety-critical systems that allows us to reduce the cost and time needed to recertify the systems as the requirements change, as their platforms change, as their implementations and algorithms change. So very important, again, for people doing safety-critical systems in medicine, national security, air traffic management, air flight, and so on. driverless cars, you name it, things that really matter. Next topic that I'll go into a bit more detail is software construction through composition. Obviously, we've been doing software construction through composition for a very long time. This is something that started decades ago, and object-oriented programming and component middleware and model-driven engineering are all examples of things in this space. But what we're really trying to do at this point is do these kinds of things at scale, do them in a much more heterogeneous way, and do them in a way that allows us to be able to kind of certify as you go. So you can build systems out of pieces where the composition is actually more reliable than any of the pieces in isolation. And I'll talk a bit more about that when we get to that part. From the point of view of the architecture paradigms, one of the key areas are these societal scale software systems. And the idea here is to not just think about technology in terms of software in our traditional way and hardware in our traditional way, but really start thinking about what happens when people get in the mix. And as we all know, one of the biggest challenges in any type of project is trying to get people to work together effectively. I always joke that the software projects course that we do here at Vanderbilt, which is a senior level course, is really mostly about teaching students why working in teams is hard. Because you have people and they have their own idiosyncrasies and they don't understand things in the same way. They don't always pull in the same direction. So if you think about that on steroids for societal scale software, it's very challenging to get this to work right. And I think you can see what's happening in the world today as a good example of this, with some of the challenges with Facebook or Meta and privacy concerns and so on and so forth. This idea of engineering AI-enabled software systems is really thinking about not just using software tools, not just using AI for software tools, but using AI in order to be able to develop software that does things intelligently and makes predictions and tries to analyze information in ways that a human or groups of humans might not think about as quickly. And obviously, this is an area that's fraught with opportunity and peril for all kinds of obvious reasons. And then the last piece of the puzzle, which we really won't talk much about today, is engineering quantum computing software systems. So not just thinking about the hardware and the algorithms, but thinking about what kinds of programming languages, what kind of platforms, what kinds of middleware, how are we going to be able to leverage these things? How are you going to program a quantum computer? Will it be like programming a very large-scale multi-core computer or a distributed cluster, or will it be completely and totally different? And naturally, the jury is still out on all of those issues. So let's start doing a little bit more of a deep dive into some of these topics. And we'll start out first with AI augmented software development. This is something that you'll probably see more and more of over the next decade as researchers and developers get further along in being able to take ideas that are currently in research labs and get them transitioned into commercial practice. Most likely in things like open source platforms very quickly, because that's where the community will get a chance to work together. So basically what we want to be able to do is we want to be able to leverage advances in deep learning and transformers and search-based algorithms and so on to support the development of next-generation software tools for design, evolution, conformance that can basically enforce good software principles in system development in a more automated and reliable way than we do today by hand. And this, of course, is going to require thinking through the different stages in the software lifecycle and where AI makes the most sense. And some places it's going to make sense probably faster than others. For example, as we'll see in the next couple of other topics, I'm convinced that applying a lot of these tools for quality assurance and testing is going to be crucially important, because those are areas where current techniques don't always scale up very well, and there's lots of opportunities to leverage intelligent tools to find defects in ways that perhaps people have a hard time trying to do. Another key goal of the research here is to figure out what's best done by humans versus what's best done by computers. And again, it should be pretty clear from the last couple decades of automation of software development and software testing and validation that people are good at creative things, but they tend to get sloppy, they tend to be forgetful, they tend to do stuff where a computer is often better because it's more patient, or you can throw a lot more resources at the problem to continually run regression tests, to try to be intelligent about what tests to run, and those kinds of things. So trying to figure out who does what is going to be a big part of this research agenda. We'd also like to raise the level of programming so that rather than thinking about the bits and bytes and the third generation language features like loops and conditional statements and methods and classes and so on, you can think more about expressing what your requirements are in a manner that a computer system and a pipeline of software transformers can convert from human statements of intent into working software that captures that intent effectively. And that turns out, of course, to be a devilishly hard thing to do because natural language is very imprecise often, and that's why we have programming languages, because they're a lot more precise. But trying to find a way to bridge that gap is going to be important. What I think we're going to be doing here is coming up with new ways of doing software where more and more of that may be handed off to tools, especially on the quality assurance front, and allow us to rethink the software development lifecycle. You could imagine a world, for example, where you just continually rerun assessments of your quality 24/7 using AI-guided tools to do a more effective job of doing coverage of your code. You can think of ways of being able to have your wizards be smarter about trying to suggest you alternative architectures or alternative distribution models or alternative application of different kinds of patterns that could be then automatically translated into different approaches, and then you could benchmark them automatically to see which ones work most effectively while still maintaining the requirements from a functional perspective. How do you get user intent? This, again, is devilishly hard. People have been trying for decades to raise the level of abstraction for programming. I think we've done a pretty good job, but it's not as easy as Star Trek, where you just speak into the computer and it does your bidding without you having to do much beyond just state what you want. We also have to think about how we model the software lifecycle workflows using AI. What are the formalisms for doing this? Will traditional ways of ontologies work effectively? Do we need to think of new ways of representing knowledge so that we can automate it and extract information from it at appropriate places? And then I think the crucial part, which is a good segue into the next topic, is how do we accumulate evidence in an AI-driven world? One of the hardest things about AI-based approaches is they produce results, but it's often unclear how or why they got to those results, because the normal chain of custody that humans would do is often not carried through as intuitively in an automated and artificially intelligent driven way. So we're going to have to, if we want to build safety critical or mission critical systems using these kinds of tools, we're going to have a better way of maintaining and producing and then analyzing the evidence in an automated way that's understandable. And then, of course, this leads into the next topic, which is how do we orchestrate continuous systems evolution? So another key topic that's described in detail in the report has to do with how do we assure continuously evolving systems. Now, this is a big deal no matter what kind of system you're dealing with. Unless you build a one-shot throwaway piece of software that will never change and you use it for a day to demonstrate some examples to your students, which I do all the time in my classes, unless you're doing something like that, you probably need to think about the software lifecycle. And the more you get into mission critical and safety critical systems, the more important it is to be able to produce evidence that the system behaves the way it's intended, that it meets its requirements. And this is particularly true in certain areas, healthcare being one of them. Nuclear weapons or nuclear reactors are also another good example where the right answer delivered too late becomes the wrong answer. Air traffic management systems would be another good example. The global telecommunications system. You don't want to just make changes willy-nilly and keep your fingers crossed that everything is going to work effectively. And especially as these systems not only evolve continuously, but actually have dynamic properties that adapt at runtime, wow, that really gets complicated very quickly. And if we want to do this effectively, we have to think about both the functional features as well as the quality attributes, the non-functional properties, the things that those of us in the middleware community have thought about for decades, things like dependability or reliability or predictability or scalability or securability or resilience or whatever you want to talk about that has these quality attribute properties. So the research advances here are really going to take place, we think, in two areas. One is the theory of evidence, and the other is the theory of evolution. And the theory of evidence really comes down to how do you create artifacts that will give people, usually certification agencies, confidence that what's being developed actually meets the requirements and won't go off the rails, literally in some cases, like a train system, or won't cause cars to crash into each other, or won't cause the nuclear reactor to melt down or whatnot. And historically, this has been done in a very time-consuming way using things like formal proofs of correctness, or more recently, things like assurance cases, where you try to reason about properties of the software and the system you want to be involatile so that you can always maintain these invariants. And historically, this has been a very, very time-consuming and laborious process, such that when anything changes, lots and lots of artifacts have to be reworked manually, which obviously is not going to scale very well. So one aspect of the research is to try to automatically create either formal or semi-formal arguments or assurance cases that can give people greater confidence while relying on automation, which is not really how it's done at scale today. And then we also have to think about how potential changes to requirements, potential changes to environments, potential changes to implementations can propagate and lead to new failure modes or vulnerabilities. And this, of course, is where safety gets cross-cut with security. And one of the things that's really driving the innovation in the safety world is the fact that they have to be able to adapt to new security threats. Used to be you could build a safety critical system and then leave it alone for a long time, and you were pretty confident as long as nothing changed too much, you're still going to be within the safety bounds. Obviously, with modern systems where you're going to have security vulnerabilities, where they're connected to the network, where there's all kinds of opportunities for breaches and ransomware attacks and so on, you have to continually rethink and repatch these systems all the time. So that has opened up a whole new can of worms. Finding ways to leverage the AI techniques we talked about in the previous discussion to generate and analyze runtime data, generate system improvement suggestions, come up with proofs that demonstrate what's being done will lead to the appropriate outcome. Very, very important. Likewise, trying to figure out ways of combining human intent with operational data in order to be able to make change requests and assure those. Very, very important topic. So I see a lot of synergy between these approaches here for assuring continuously evolving systems as a big theme, and what we talked about earlier with kind of AI-based tools and AI-based methods. The next topic, which again is one of my favorites because it relates to what I've worked on throughout my career, has to do with software construction through compositional correctness. And the idea here is you want to be able to build large-scale systems, not small-scale systems. We have a pretty good way of dealing with building small-scale systems out of building block pieces, and we have for the last 40 years or so. But how do we build large-scale systems out of components that can be intelligently composed such that the composition we end up with that's integrated will be more robust and resilient than the component parts in isolation? A good example of this philosophy is the TCP/IP protocol, where the hops can be unreliable, but you get end-to-end reliability, where the end-to-end behavior and semantics are more reliable potentially than the hop-by-hop reliability. And we need the same sort of thing with components in modern modular software composition approaches. And the whole idea here is as you build your system, as you evolve it, as you add new pieces to it, you don't have to recertify every last piece of it when anything changes. And of course, the goal of that is to build things with the appropriate degree of isolation and boundaries and time and space partitioning and compositional correctness tools and methods so that we can bound the effort required to reassure and recertify the individual components and subsets of composed components up to the entire system. In the perfect world, we'd like to be able to have the certification process and the complexity and cost of assurance grow no more than linearly with the size of the system and the scope of the changes. Right now, that's not the case because lots and lots of things have to be retested whenever anything changes. So what do we need to make this come to fruition? We need a theory of composability that supports cross-cutting concerns and quality attributes. We got part of the way there about 2 decades ago when we were doing a lot of work on aspect-oriented programming and aspect-oriented software development. That didn't go as far as we might have wanted to, but I think there's good opportunities, and there's a lot of enhancements these days with modern tools and modern platforms like various types of dependency injection frameworks that use annotations, where you can essentially use quality attributes in a declarative way so that the system weaves together or composes large amounts of what needs to be developed. A good example of this would be the Spring platform and WebFlux and WebMVC and so on. We need to be able to have ways of being able to document the patterns and then finding tools that can enforce those patterns throughout the life cycle. Again, we're making progress there, but there's still lots that needs to be done. And we need these smart composition tool chains that can create some behaviors, can assure behaviors at scale, can integrate pieces that weren't necessarily designed to work together initially so that the composition, again, can be more reliable than the pieces in isolation. And then something else that's important, and this is a real challenge for the research community, is how do we take all the different work that's being done by different researchers at different labs, at different universities throughout the world, and find some way to be able to make things work effectively. And that's a very challenging thing to be able to do, because everybody has their own tool chain, their own semantic information models, their own metadata, their own formalisms, and trying to make those things work together is tricky. The last thing I'll talk about, and then we're going to wrap up and take some questions, are engineering of socio-technical systems. And these, again, are the societal scale systems that we're all familiar with nowadays, things like Twitter and Facebook and YouTube and TikTok and so on. And those are great in a lot of ways, but they've also introduced all kinds of challenges for global society and individual society. We have issues with ethics, people using these systems in ways that are not ethical in obvious ways. There's opportunities for bias, there's opportunities for misinformation. And the tricky part of this is that people get into the mix, and people have a way of being able to get spun up and panicked. And so the challenge with these socio-technical systems is that they have people in the mix, and therefore they're harder to assure in the classic way. So the tricky part of this research agenda, which to some extent, honestly, is perhaps the most important one of all, if you want to think about our future as a species, is coming up with ways to build and evolve these very, very large societal scale systems that enable all the benefits without having all the ethical risks of privacy, bias, trust, concealed influence, unrestrained social manipulation. And you don't have to look very far to find lots of examples of things that are having these kinds of issues in practice today. And I won't belabor them by talking about them in length, but you can imagine what they are. So what we're going to need to do here as researchers is we're going to need to work with other fields, psychologists, sociologists, economics, game theorists, and so on, to come up with ways to build software engineering artifacts and tools that will have better support for these new dimensions of system behavior and ethics. Another thing that's really tricky is, as you've no doubt noticed, is how do you do experimentation on these systems that's realistic without causing a panic in its own right? So obviously large social media companies continually do experiments on their users through A/B testing, but that oftentimes gets people very upset. I just saw the other day that apparently you can upload naked pictures of yourself to protect yourself from revenge porn. This is not necessarily, doesn't sound like it's necessarily a good idea in some ways, because that has other kinds of issues. So we have to think very carefully about how these systems get applied for all kinds of obvious reasons. So we need new attributes, we need new quality properties, architectures, tools that account for people. We need to have a new theory of socio-technical epistemology, which is another way of saying, how do I know what's actually true? And that's a very difficult issue because it's not just about technology, obviously. And we need to be able to balance trade-offs between various quality attributes, including conformance to policies. And a lot of these policies will also be country-specific or region-specific, because different countries have different rules and different regulations that need to be enforced. As you've no doubt noticed, if you've tried to access content in YouTube from different parts of the world, certain content is available in some places and certain content is not. And of course, we have to find a way to try to protect against misuse of these platforms. So to summarize what I've been talking about today, the changes that we describe in our findings in the study will show that software approaches will profoundly impact everything that we're doing because we rely on this stuff. This is going to require us to think about new domains that researchers like ourselves have to become fluent and expert at, such as automation, reassuring, continuously evolving mission safety critical systems. How do we understand system composition and intelligent composition at scale? What are new types of systems? A lot of these systems are very heterogeneous, so it's difficult to find one language, one platform, one tool chain that will do it all. We have to think about a broader range of issues than just the technology. We have to think about things like transparency, freedom from bias, privacy, and these are ever-changing issues that have a lot to do with the legislative process and the influence process in countries around the world. This is not going to be something that we as researchers can do on our own. We need to get involvement with industry. We need to get involvement with government in order to make sure that we can work on the right kinds of problems at scale. It's my fervent belief, after doing lots of interdisciplinary work over the past decade at Vanderbilt University, that there's a lot of great opportunities for research when we start thinking beyond our traditional stovepipes and traditional disciplinary boundaries. Healthcare, transportation, power, those kinds of things come from working with others and not just working by ourselves. Thinking about the more global issues, we have to think about how we can team up with researchers around the world. These are not problems that will be solved easily. No one group has the corner of the market on funding or technology or talent to make it work. And speaking of talent, we need to find a way to be able to leverage the global workforce, because there's more than enough work to go around for everybody. Even if we use AI automation to automate some of the stuff that was done manually, there's still just going to be more and more things at new levels of abstraction that will require our expertise and our attention. So that's the end of my prepared remarks. I'm happy to take questions.